simple matrix. A square matrix A is called diagonalizable if there is an invertible matrix P such that P inverse AP is a diagonal matrix, then the matrix P is said to diagonalize A. How to check whether matrix A is diagonalizable or not? First, A is diagonalizable if the number of distinct eigenvalues is equal to the size of the matrix, or the number of bases for the eigenspaces is equal to the size of the matrix. Now, let's look at an example of a diagonalizable matrix. Suppose that we have a matrix A size 2 by 2 given by 1, 0, 6 and negative 1. We need to compute the matrix for A minus lambda I and find the determinant. In this case, the polynomial equation is 1 minus lambda and negative 1 minus lambda, which give us two value of eigenvalues, which are 1 and negative 1. As we can see in the slide, the size of the matrix, which is 2 by 2, is the same as the number of distinct eigenvalues. Hence, matrix A is diagonalizable. Now, let's look at an example of a non-diagonalizable matrix. Suppose that we have a matrix size 2 by 2 given by 1, 1, 0, 1. We use the same method as before, which we compute the matrix for A minus lambda I and find the determinant. In this question, we only get one eigenvalue, which is equal to 1. Before we conclude that this matrix is not diagonalizable, we need to check with another method, which is using the eigenvector. So we use the value of lambda equal to 1 to solve the system of linear equation. As we can see, the system of linear equation has infinitely many solutions because of the existence of free variable in X2. We then find the basis for the eigenspace corresponding to lambda 1, which is 0 and 1. Since we only have one basis or one eigenvector, which is not equal to the matrix size 2 by 2, hence this matrix is not diagonalizable.
To begin finding matrix P, we start with the eigenvalues of matrix A. We do this using characteristic equation, that is determinant A minus lambda I equals to 0. Here, I is the identity matrix and lambda represent the eigenvalues. Solving this equation will give us the eigenvalues as given in this slide. Once we have the eigenvalue, the next step is to find the eigenvectors. For each eigenvalue, we solve the system in bracket A minus lambda I multiplied with x vector must be equal to 0. The non-zero solutions to this equation give us the eigenvectors, which we label as P1, P2 and so on. Each of these eigenvectors forms a basis for the eigenspace of the corresponding eigenvalue. Finally, we form matrix P by placing the eigenvectors as columns as given in this slide. It is important to make sure these eigenvectors are linearly independent, because only then will matrix P be invertible, which is often a requirement for diagonalization. Let's look at example 1 here, where we are given the matrix A equals to 4, 0, 1, 3. We start by using the characteristic equation, that is determinant A minus lambda identity equals to 0. And then we substitute matrix A, and finally we get the eigenvalues lambda equals to 3 and lambda equals to 4. Next, for lambda equals to 3, we need to find the vector, and we get the eigenvector P1 equals to negative 1, 1, and for lambda equals to 4, we get the eigenvector P2, 1, 0. Finally, we can form matrix P using the eigenvectors as columns. And that's how we find the eigenvalues, eigenvectors and form matrix P for diagonalization.
So today I'll explain on how to diagonalize the matrix A by finding a diagonal matrix D using eigenvalues and eigenvectors. So we're going to use formula D equals to P inverse AP, which is A is the original matrix, P is a matrix made of eigenvectors as its columns, and D is a diagonal matrix with eigenvalues on its main diagonal. So, to form a diagonal matrix D using the formula D equals to P inverse AP, we got a few steps. For the first step, we need to have the eigenvalues. So, I already show you the calculation on how to find the eigenvalues. We got here lambda equals to 4 and lambda equals to 3. The next step is to find the eigenvectors, and from the last example I already show you on how to calculate the eigenvectors. So for the lambda equals to 3, we got the eigenvectors is -1 1, and for lambda equals to 4, we got eigenvectors is 1 0. So the next step 3, is to construct the matrix P. So place the eigenvectors as columns of matrix P in the same order as the eigenvalues. So we got P equals to -1 1 1 0. So the next step is find the P inverse. I already show you here the calculation on how to find the P inverse. So P inverse we got 0 1 1 1. And the next step is step 5 using the formula. First, I divide the step 1 to step 2. First, we need to find the A multiplied by matrix P multiply, and we got that. Next to the step 2, the P inverse multiplied by AP, and then we're gonna get that, and that's all. We got D. Boom, 3004.
And now for application of diagonalization matrix. First, what is matrix power? If we have a square matrix A, then A to the power of K means multiplying A by itself K times. But manually calculating something like A power of 10 or A power of 999 takes a lot of time and effort. That's where diagonalization help. We just need to find the information of matrix P, diagonal matrix D, then find inverse of P, and raise the diagonal matrix D to the power of K, which is easy since you just raise the diagonal values. Finally, we multiply everything. P multiplied by D power of K multiplied by inverse of P. This gives us A power of K quickly, especially for high power. Now let's see how diagonalization helps in finding matrix power. There are 3 simple steps. First is diagonalize matrix A. This means we find two matrices P and D such that A equal to P multiplied by D multiplied by inverse of P, which P contain the eigenvectors and D is a diagonal matrix of eigenvalues. Then for step 2, we compute D power of K. Since D is diagonal, we just raise each diagonal entry to the power of K. This is very easy and fast compared to multiplying big matrix. Then for step 3, we compute A power of K using the formula A power of K equal to P multiplied by D power of K multiplied by inverse of P. In example 2, we are using diagonalization to find the power of a matrix A power of K. So for the step 1, we already have matrix P and diagonal matrix D, which is P equal to matrix -1 1 1 0, and for D is matrix 3 0 0 4. Then for step 2, we need to find the inverse of matrix P. Using the inverse formula for 2 by 2 matrix, we get P power of -1 equal to matrix 0 1 1 1. Then we calculate D power of K. Since D is diagonal, we just raise the diagonal value to the power of K. So D power of K is matrix 3 power of K 0 0 4 power of K. Step 3, now we use the formula A power of K equal to P multiplied by D power of K multiplied by P inverse. Then we multiply the 3 matrices in order. After multiplying everything, we get the final result for A power of K.
And now we want to find A power of 10 by using formula A power of n equal to P D power of n P power of -1. So we just substitute the n equal to 10. So for D power of 10, we get matrix D 3 power of 10 0 0 4 power of 10 equal to 59049 0 0 1048 576. So we just put into formula
and the answer we get is A power of 10 equal to 1048576989527059049.